Hi, my name is Sarah Overby. I'm a 2020 MDF Fellow, and I'm currently doing my PhD at the University of Valencia in Spain in the Translational Genomics Lab. In our lab, we study myotonic dystrophy type 1, and we principally study the use of antisense oligonucleotides to give therapy to patients. So here I wanted to describe a little bit about my findings. Just a quick overview of the disease. As you know, DM1 is caused by toxic repetitions found in the DMPK gene, and when these repetitions are transcribed into RNA, the MBNL family of proteins bind with super high affinity to these repetitions, and it deprives them of their functionality. The MBNL protein family is very important for post-transcriptional splicing regulation and polyadenylation, and so without their function, many transcripts are misspliced in the disease, and because of these missplicings, this also leads to downstream symptoms of the disease such as myotonia, muscle weakness, etc. So something that our lab is very interested in studying are the role of microRNAs in DM1. As a little overview of microRNAs, they are very small pieces of RNA, single-stranded DNA, single-stranded RNA that bind to the 3' UTR of mature messenger RNA transcripts. And when they bind to the 3' UTR, this allows them to regulate its transcription into protein. So typically, there's more microRNAs bound to the 3' UTR, the less protein you will see of that transcript. So we were curious to know which microRNAs were regulating MBNL proteins, and this was found by one of my colleagues to be microRNA 23B and microRNA 218 of principal interest. And for her, she designed some antisense oligonucleotides to see if the binding and repression of the microRNAs would allow the transcripts to produce more MBNL as sort of a backdoor method, and therefore compensate for the MBNL that was already sequestered into the repetitions. So this is something that's already been shown and had really great success with antagomeres, and the antagomeres are little antisense oligonucleotides, which are just small pieces of RNA as well that will complementary bind exactly to the region of interest. So for us, the region of interest was microRNA 23B, for example. She designed antagomeres that directly bind specifically to those microRNAs, therefore they couldn't bind to the MBNL transcripts, and that way the transcripts could make protein and compensate. For my thesis, I wanted to build on this idea and improve it if possible by using the same sort of antisense technology, but instead of binding directly to the microRNAs, I wanted to have them bind to the binding sites and thereby block the binding of microRNAs. So we designed block mirrors that are just small pieces of RNA that are antisense oligonucleotides that bind just specifically to the binding sites of the microRNA 23B. And that way, the microRNA cannot reach this site and therefore cannot regulate the transcript, and therefore more MBNL protein can be translated and go back into the cytoplasm of the cell and perform its function. So we worked with the University of Oxford in designing these oligos. First, we wanted to make sure that they would be able to penetrate the cell, because one of the difficulties in antisense oligonucleotide therapy is getting the cell to accept the therapy. So they have some exciting cell-penetrating peptides that we linked to the sequence that we were interested in, and a PMO morpholino, which is a very stable version of the antisense oligonucleotide, and that therefore created the PPMO block mirror, is what we like to call it. And this created a very stable compound, and a compound that would be likely to be accepted by the cell. So first we wanted to try them in DM1 cells in vitro, and the first we want to take a look is make sure that they are non-toxic, and because they have cell-penetrating peptide technology linked to the oligos, this allows you to transfect them in cells without the use of transfection reagent. This is advantageous because transfection reagent can sometimes be a bit toxic. And so as you can see here, even with the increasing concentrations the toxicity stays the same. It's just there's no toxicity at all, and this is most likely due to the fact that the cell-penetrating peptides are very non-toxic. After that, we also looked at the transcripts of MBNL1 and 2 and saw that they were being expressed more after transfection with the block mirrors. Most exciting as well is we saw a huge increase in the fluorescence of MBNL proteins. Here you can see these are healthy people, which the green is MBNL proteins and the blue are the nuclei. In DM1, you can see that there's hardly any fluorescence in the cytoplasm, and if you look closely, there are some small foci where the MBNL is trapped in the nucleus. After treatment with the block mirror, you can see there was a full restoration of the subcellular localization of MBNL1 and also in the fluorescence. Fluorescence was quantified here and it was significantly higher, and it's exciting to see that it's back in the cytoplasm where it can perform its normal function. Then we noticed that after treatment, the MBNL also was increased, but not only was it increased, it was also functional in that it was being able to produce the correct splicing patterns for certain transcripts, for example, MBNL1 exon 5 and infix exon 7. So with the success of this treatment in cells, we decided it was time to move to mice. We use HSALR transgenic mice for DM1 therapy. And first, of course, we want to make sure that they are non-toxic to the mice. After treatment, all of the biochemical parameters were within the normal range. As you can see, it looks a bit low on the creatine protein kinase parameter, but after looking at the results, they were within normal range. Also, for this particular parameter, it's more dangerous. Let's say it's more of interest if this parameter is increased. That's when you can find toxicity, but because it was lowered or decreased, there's really no reason of concern. So all of these were within normal levels. And another exciting physiological feature that we noticed after treatment was the increase in grip strength. We use the mice and we have them grip a bar and pull the bar to analyze how strong they are, and there was an increase after treatment. Finally, we found an increase in protein after using Western blot, a simple Western with chess. And the protein was functional because you can see here the rescue in many of the splicing patterns that we see in the mice, such as ATP2A1, CLCN1, MBNL1, and NFX. ATP2A1 is related to calcium metabolism in muscle cells. CLCN1 is directly related to myotonia, and MBNL1 exon 5, as I've spoken about before, is directly related to the subcellular localization of MBNL. And so all of these rescues and splicing pattern switches were really exciting and good indicator that the MBNL is functional again. So these oligonucleotides have been really successful, and we're in the process of publishing and patenting them as we speak. I hope to be able to test them more in preclinical trials, such as doing a dose response in mice and etc. And hopefully, if need be, we can keep working with Oxford to optimize the compounds and make sure that they are at the best design possible. I've really enjoyed being an MDF fellow here. Would not have been able to do all of this research if it hadn't been for the fellowship that I was awarded last year. The amount of guidance and support that we have from the directors, and as well as for me especially the conference I got to go to last year and meet patients, really motivates me, really inspires me to keep going at it, to never give up, and that there are real people that could benefit from this treatment. And so I'm very motivated by the support of this community, and I hope to be able to use all of this research in the future for the treatment of this disease or other diseases, because this antisense oligonucleotide treatment is the future for many rare diseases. So no matter what comes out of this research will be useful for many people to come. And I thank you for funding me and for listening to my research. Thanks very much.